Okay, so what we're doing today is we're using the equilibrium constant. The syllabus outcome for this is perform calculations to find the value of KEQ and concentrations of substances within an equilibrium system. Use these values to make predictions on the direction in which a reaction may proceed. So make sure you've gone through and done those revision questions. I'm going to go through the answers now. So the reaction coefficient Q measures relative amounts of products and reactions present at any point in time in a reaction. If Q equals KEQ, then the reaction is at equilibrium. If Q is greater than KEQ, then the reaction will move towards the reactants. And if Q is less than KEQ, then the reaction will move towards the products. Now, what we're doing today, we're going to be using the equilibrium constant. Now, once we know the equilibrium constant for a certain reaction, it can be used to calculate the concentrations of reagents at equilibrium. So, how much product's going to be there, how much reactant's going to be there at equilibrium. But to do this, we need to use an ICE table. So the first thing we're going to do this lesson is learn how to use an ICE table. ICE stands for initial, then change, then equilibrium. So it's a nice little table that we can fill in the information that we got, and we can use that to figure out the concentration of products and reactants at equilibrium. So this information gives us a way of calculating what we need. So here's an example of an ICE table. So we've got reactant 1, reactant 2, product 1, product 2. And at the left side, we have 3 rows, initial, change, and equilibrium. So what do we do in each of the rows? Firstly, in the initial row, that's the concentration of reagents that are in the reaction vessel before reaction is taking place. Okay, so you can imagine that you have a reaction vessel where you've got an equilibrium thing going on. You suddenly add in a whole bunch, of stuff, and before any collisions occur, before the reaction takes place, before there's any change in concentration, that's our initial amount. Okay, so it's before any reactions have occurred. Lastly, we have the equilibrium value. So that's the concentration of our reactants and products that is at the end of the reaction. So after all the collisions have occurred, once a dynamic equilibrium has been set up, that's what our final concentrations are going to be. And change is the difference between the initial concentration and the equilibrium concentration. So for example, if you start off with 4 moles per liter of reagent 1 and you end with 2 moles per liter of reagent 1, that's a change of -2. Don't worry too much, we will go through actual specific examples very shortly. So imagine in a reaction vessel, we had 3 moles per liter of nitrogen gas, 1 mole per liter of hydrogen gas. They're allowed to react and come to equilibrium following the equation. Again, this is a favorite of ours, the Haber process. So 3 hydrogens plus nitrogen is an equilibrium with 2 ammonias. Now, the equilibrium concentration of hydrogen is 0.1 moles per liter. So we have to use this information to fill in an ICE table. How do we do that? Well, we highlight the important information in our question. So we had in a reaction vessel 3 moles per liter of nitrogen gas, 1 mole per liter of hydrogen gas, and they're allowed to react and come to equilibrium following that equation. We also have equilibrium concentration of hydrogen of 0.1 moles per liter. Okay, so that's all of our important information, everything we need to answer this question. So we want to use this information to fill in an ICE table and find the equilibrium concentrations of all of our products. So let's put the information in. So this is what we've got. We were told we put in 1 mole per liter of hydrogen, 3 moles per liter of nitrogen, and we end with 0.1 moles per liter of hydrogen. So that's what we've got. Now, because nothing in the question mentioned putting in ammonia at the start, ammonia starts at 0. Okay. Now, how do we figure out the rest of the concentrations? Well, firstly, what we do is we know one of them, we know the initial amount and the equilibrium amount, so we can find the change. Okay, so what's the change between 1 molar and 0.1 molar? It's negative 0.9. Okay, so we start at 1, we take away 0.9, we end at 0.1. Now that we've got one of the changes, we can use that to calculate all the changes should be in a ratio that's the same as the stoichiometric ratio of the reaction. So if we lose 0.9 moles per liter of hydrogen, how much nitrogen and ammonia are we going to lose or gain? Well, if we use 0.9 moles of hydrogen, it stands to reason that we will also lose 0.3 moles of nitrogen. Okay. If we lose 0.9 of H2 and lose 0.3 of N2, they are reactants that are getting used up. When reactants get used up, they produce products. So it's going to produce some ammonia. How much is it going to produce? Well, if nitrogen has a stoichiometric ratio of 1, ammonia has a stoichiometric ratio of 2, you can safely assume that it's going to increase by 0.6. Okay. Now, once we've got the changes, we do the top row plus the middle row should give us the last row. So 3 plus negative 0.3 gives us 2.7. 0 plus 0.6 should give us 0.6. Like that. Okay, it's just that process over and over again for ice tables. Okay. Let's use another example. So in a 5-liter reaction vessel, 3 moles of N2O5 was allowed to react and come to equilibrium following the equation, that one there. So 2N2O5 is in equilibrium with 4NO2 plus O2. If the equilibrium concentration of O2 is 0.25 moles per liter, use this information to fill in an ice table. So again, that's what our ice table is going to look like. So we have the reactants and the products. Let's highlight all the important information. We had a 5-liter reaction vessel and 3 moles of N2O5. So remember, for our K equations, we need to have concentrations, which is moles per liter or moles per volume. Now, that's allowed to react and come to equilibrium. And the equilibrium concentration of O2 is 0.25 moles per liter. So let's have a look at what we've got. So we started off with 0.6 of N2O5 because that's 3 divided by 5. And the question didn't mention anything about having any NO2 or any O2 in it. So we're going to say that they're equal to 0. Okay. Now, if it doesn't mention it, then it should be 0, usually. Okay. And we're also told that the equilibrium concentration of O2 is 0.25. So what's gone on here? What information can we glean from this? Well, we can see that O2 has gone from 0 to 0.25. Sorry, just put all the answers in at once. So that means it's gone up by 0.25. So the change should be plus 0.25. If we then have one of the changes, so we can apply it to the other changes. So if O2 goes up by 0.25, it stands to reason that NO2 will go up by plus 1 because it's going up by 4 times the number of moles. And if those two are going up, our N2O5 is going to be going down. How much is it going to be going down by? Well, the stoichiometric ratio is 2, so it'll be going down by 0.5. And then we get those concentrations at equilibrium. So we get 0.6 take away 0.5 gives us 0.1. 0 plus 1 gives us 1. And 0 plus 0.25 gives us 0.25. Now, so that's just basic ice table stuff. And we will have to practice that a bit more. But what we do, why we need ice tables, is we use them a lot when we're trying to calculate the concentrations at equilibrium given the KEQ value. Okay. Now, we set up the questions with an unknown change in concentration, okay, because we're trying to find out the final concentrations of the reactants and products. Um, we then use that value to then solve for x, to solve for our unknown. Now, we'll do a few examples just so you make sure you know exactly what you're doing, but there's also some things along the way that I need to point out, but I'll do that in time. So, have an example. Here's an example. In a 4-liter reaction vessel, 1 mole of N2 and 2 moles of O2 was allowed to react and come to equilibrium following the equation O2 plus N2 is in equilibrium with 2NO. If the KEQ for this reaction is 2.4 times 10 to the negative 5, determine the equilibrium concentrations of all reactants. Okay, so what do we have to do? First step, highlight everything that's important. So we had a 4-liter reaction vessel, 1 mole of nitrogen, 2 moles of oxygen. That's our reaction equation, and our KEQ is 2.4 times 10 to the negative 5. And what we're trying to do is determine the equilibrium concentrations of all reactants. So that's reactants and products. So we take the information that we've got and we put it into an ice table. So remember, it was 1 mole in 4 liters, so 1 mole of nitrogen in a 4-liter vessel, so we get 0.25 moles per liter of nitrogen. And we had 2 moles in 4 liters for oxygen. So that's why we got a concentration of 0.5. Nothing was mentioned about NO, so we can safely assume that there was none there to begin with. Now, how's it going to change? What we do is we put in a pronumeral to represent the change in concentration, and we times it by the stoichiometric ratio. Okay, so we can see there that O2 and N2 go down by a factor of x, NO goes up by a factor of 2x. Okay, and so at equilibrium, the concentration of O2 is going to be 0.5 take away x. Concentration of nitrogen is going to be 0.25 take away x. The concentration of NO will be 0 plus 2x. So it'll just be 2x. Now, that last line, that equilibrium value, they're the ones that we put into our K equation or K expression. So we solve for the unknown. So we've been given KEQ value in the question, and we now get that. So we've done the K expression, we've substituted in our unknowns, and we've made it equal to our KEQ value. Okay. We then start to, we can solve it mathematically. Anyone that's in advanced or extension, if you want to solve this using quadratic formula, feel free. But there are some things that we can do to it to make it a bit easier on ourselves. So before we solve, if mathematics is not your strong point, remember that you do get marks in the HSC for trying. I have been trying to point this out a fair bit, provides relevant information. It's usually enough to get 1 mark. In 2019, there was an ice table question that had 2 out of 4 marks for provide some relevant steps. So that's probably enough to, if you write down your ice table and start to plot things out, 2 out of 4 marks. You don't even have to get it right at that point. Yeah, so if you correctly set up your ice table and substitute into the K equation, you're likely to get at least 2 out of 4 marks. So it's better than just leaving it blank. Okay. Now, solve for the unknown. When solving our ice table questions, we can introduce an assumption that vastly simplifies the working out. Okay, it removes the need for solving that quadratic equation. Now, the assumption is that if x is much less than y, then y take away x is approximately equal to y. Now, what do we mean by this? Well, let's use some actual numbers as an example. If x is 0.01 and y is 50, 50 take away 0.01 is very close to 50. It's going to be like 49.999 or something. Okay, it's a number that is very close to 50. And so we can just keep that assumption. Now, I want to point out that it's preferable to use the assumption in the HSC. At university, that might be a different story. But for the HSC, it had to be made accessible to people that are doing standard maths. So that means you don't have to do quadratics. If you think you can solve the quadratic, by all means, go ahead and do it. You won't get marked down. But if you don't know how to do the quadratic, do it this way. This is the preferred way for you guys. So how do we do that? What this looks like. So we can say our KQ is equal to 2x squared over 0.25 take away x times 0.5 take away x. We can assume that our x value is going to be very small, just based on that KQ value. Okay. We can then go, okay, well, if x is much less than y, y minus x will be equal to y. So basically what we do is we ignore those x's that are taken away. Okay. So we end up with 2x squared over 0.25 times 0.5, which what we can then do, that equation is so much easier to solve. We don't need to deal with quadratics. Okay, so what we do, multiply up the numbers, expand our brackets, divide through by 4, and we get that value there. X squared equals 7.5 times 10 to the negative 7, which when we square root it gives us plus or minus 8.66 by 10 to the negative 4. Now, that's our mathematical answer. Okay, that's not our chemistry answer. What we have to do is we have to look at it in depth. So plus or minus 8.66 times 10 to the minus 4. That seems right. But in chemistry, we have to carefully observe what's happening. Okay, because again, like I was saying in some other classes, our concentrations can't be negative. So our final concentration in our ice table, if we put in one of these values and we get a negative concentration, then that's not the right answer. So here, this is our ice table that we had. So it was 0.25 take away x equals 0.25 take away x, okay? If we then substitute in our values, we should get a number between 0 and the initial number, okay? Because there's no NO at the start, so we can't increase the concentrations of O2 and N2, they can only decrease, but they can't decrease more than what's there, okay? So therefore our correct answer is plus 8.66 times 10 to the negative 4. If we put in negative 8.66 times 10 to the negative 4, we're going to end up with more than we started with, which we can't actually have because, again, there's no NO2 to produce any of the products. So X is, now this isn't the end. So I know a lot of mathematics things, you find X, that's the end of it. This isn't, X is only one part of it. We then have to go on and use that X value to find our concentrations at equilibrium. And we use this number to figure out our equilibrium concentrations. So concentration of nitrogen was 0.25 take away X, so we get 0.249 moles per liter. O2 was 0.5 take away X, which is 0.499. And the concentration of NO was 2 times X, because remember it was plus 2X in our ice table, which gives us 1.732 times 10 to the negative 3. Okay, so if you then go and take all of those numbers and put them into the K equation, we should get out that number that we had at the start for KEQ. Okay, so just a few more notes on ICE tables. So I know it's a lot to deal with, but they are quite important. Now, the assumption we made in this question is not applicable to all equilibrium systems, but it is applicable to all equilibrium systems you will be asked about in the HSC. Okay, so if you're ever asked a question where you have to find the equilibrium concentrations, you will be given a question that can be answerable using the assumption. Okay, now once you go past HSC, once you go to university, you'll have to learn the quadratic formula to answer a lot of them. Some of them you might even have to answer using some estimation methods like Newton's method of approximation, okay, for finding roots. But in the HSC, you will be able to use the assumption. You will get full marks for using the assumption. You will not lose marks for using the quadratic. It's just good to keep in mind that if you're doing independent study that's not directed towards the New South Wales HSC chemistry syllabus, so if you're not using a New South Wales textbook or you're not using my notes or anything else from New South Wales, if you decide for some reason that you want to do some VCE stuff, you will have to be careful on what happens. If you do want to do that independent study, just use the 100 test to find out if you can use the assumption. Now, that 100 test is if the concentration of the reactants divided by the KEQ value is greater than 100, then you can use that assumption. Okay. So let's have a look at this one. So again, this is going to be one where we can use the assumption because this is the only ways that I'm going to show you. If you want to do the quadratic method, you can come see me out of class. So reaction vessel initially contains 2 moles per liter of hydrogen, 0.5 moles per liter of carbon monoxide, and the mixture was allowed to react and come to equilibrium following the equation, this one. So carbon monoxide plus 3H2 is in equilibrium with methane plus water. Now we can see that they're all gases, so they're all going to be included. So what do we do? Let's write out our ICE table for this in just a sec. Our KEQ value given is 3.4 times 10 to the negative 3. And we're asked to determine the equilibrium concentration of hydrogen. So this is important because it's telling us exactly which one we need to find. We don't need to find all of them, just this one particular concentration. So reaction vessel initially, so this is at the start before equilibrium occurs, has 2 moles per liter of hydrogen and 0.5 moles per liter of carbon monoxide. That's our reaction equation. It says 1 to 3 to 1 to 1. And if the KEQ for this reaction is 3.4 by 10 to the negative 3, determine the equilibrium concentration of hydrogen. So, what do we do? Set up our ICE table. Start filling it in. We were told the initial amounts of carbon monoxide and hydrogen, okay, which also implied that the other ones started at 0. So our carbon monoxide starts at 0.5, hydrogen starts at 2, methane starts at 0, water starts at 0. So we can see immediately there that all of the reagents are going to shift away from the reactants and go to the products because our products can't go below 0, so they're going to have to increase. Looking at the stoichiometric ratios, carbon monoxide, hydrogen go down, methane and water go up. Now carbon monoxide goes down by a factor of X, hydrogen goes down by 3X, methane goes up by 1X, water goes up by 1X. So our equilibrium concentrations are 0.5 minus X, 2 minus 3X, X, and X. We then write down our K equation. So in this case, it's CH4 times H2O over carbon monoxide times H2 cubed. We then need to substitute in our values. Okay, so X times X over 0.5 minus X times 2 minus 3X cubed. We then apply the assumption. So remember, the assumption is when X is much smaller than Y. Y take away X is approximately equal to Y. So in this case, X is going to be small enough that if we take it away from 0.5 and if we take it away from 2, it's not going to change them all by that much. Now, we substitute in our values, simplify them as best we can, multiply up the 4, and then we square root the answer, so we get x equals 0.117. Again, we have to have a look at the direction in which it's all going. Okay, so x is not our answer, it's part of our answer. We then have to go and use it. So we're looking for the concentration of hydrogen at equilibrium. So hydrogen at equilibrium, we have the equilibrium expression as 2 minus 3x. So that's 2 minus 3 times 0.117, which gives us 1.65 moles per liter. And then that's our equilibrium concentration of hydrogen. Okay. Now, example 3. A 100-liter reaction vessel initially contains 40 moles of hydrogen, 30 moles of nitrogen. The mixture was allowed to react and come to the equilibrium following this equation. If the KEQ for this reaction is 1.52 by 10 to the negative 6, determine the equilibrium concentration of ammonia. So can I get you guys to pause the video, have a go at that, follow the exact same procedure that we've been doing. So create an ice table, fill out the ice table with unknown changes, and use algebra to figure out the final value there. So, so a 100-liter reaction vessel initially contains 40 moles of hydrogen, 30 moles of nitrogen. The mixture was allowed to react according to that equation. And the KEQ for this reaction is 1.52 by 10 to the negative 6. So we want to determine that equilibrium concentration of ammonia. So what do? We take our ice table, we fill in all the information that we have. So we know that the concentration of N2 is 0.3, H2 is 0.4. Now let's remember 30 moles in 100 liters. So that's how we get those values. Now it mentions nothing about ammonia, so we're going to assume there's none there. What's going to happen? Well, because ammonia starts with 0 concentration, we're going to get some ammonia being produced. So we're going to take away X of nitrogen, take away 3X of hydrogen, and we're going to add 2X of ammonia. So that's going to be our equilibrium concentrations. Start off with our K expression. So ammonia squared over nitrogen times hydrogen cubes. So it's 2x all squared over 0.3 minus x times 0.4 minus 3x cubed. Now, we're going to apply the assumption because that's what we can do. And we get 2x all squared over 0.3 times 0.4 cubed. Gives us this number, multiply up the 0.0192, divide by 4, take the square root. Again, it can be plus or minus. It's pretty much 99% of the time going to be plus. And so because we're looking for the concentrations of ammonia at equilibrium, concentration of ammonia is 2x. We found x to be 8.54 by 10 to the negative 5. So the concentration should be 2 times that number, which is equal to 1.71 times 10 to the negative 4 moles per liter. So, in summary for today, to calculate concentrations at equilibrium, you need to use an ice table. ICE stands for initial change equilibrium. After substituting in our expressions for the equilibrium concentrations, we solve for x. And remember, we can use that assumption that if x is much less than y, then y minus x should be approximately equal to y. And that should simplify our equation. Okay, so please have a go at the rest of those. Any issues, please come and see me. We'll probably spend 2 whole lessons on this just so you make sure that you're understanding what's going on. Okay. And that is all for today. Thank you.